So day 10 of Advent of Code sets up an interesting problem. you you have all of these voltage adapters in your bag and not voltage, I'm sorry, joltage. Joltage adapters. And each joltage adapter can increase the joltage from its input to its output by as much as 3 jolts. Now, the way they state this in the problem, and I'll show this to you here, is that let's see, where is it? It's here. Oh yes, any given adapter can take an input 1, 2, or 3 jolts lower than its rating, right? So if you plug 2 adapters together, the one on the left will have a lower rating than the one on the right. Okay, now what that means is that if you plug them all together, it's the same as just sorting the list of output voltages. And by the way, that's what the input data is. The input data is the list of output voltages of the adapters in your bag. And the problem is asking us to assemble them in order, right? Plug them all into each other and then measure the differences in the joltage between each, and then count the number of differences that are 1 apart and count the differences that are 3 apart, multiply those numbers together to give you the answer. For example, here they show a list of joltage adapters in your bag, and they walk through the way that you would arrange them, which simply is sorting them, by the way. And then you find that you have 7 differences of 1 and 5 differences of 3. And then they give you a larger example here. We will use these as our acceptance tests. And in the larger example, there are 22 differences of 1 and 10 differences of 3. And you multiply those two together to get a 220, and that would be the answer to this problem. Okay. Right, so here's the final result. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? And that's what you've got to put in here. Okay, so let us begin. Let's see, where should we begin here? Well, let's go over here and we will say line new speckle J day 10. All right, so we're going to create a new project, of course. All right. And we're going to go to IntelliJ, bring up IntelliJ, and we will get rid of day 9. Oh, we've already gotten rid of day 9. So we'll create a new project from existing sources, and we will go to day 10, which should already be created for us. Yes, and we will use the project kludge to open. Lovely. Okay, okay. 1.8. Okay, okay. Lovely. There's our project. We've got a spec. We've got sources. Yes, thank you for the tip. Let's add a configuration for line again. There it is, line again, and it's going to be named auto, and we're going to say spec-a, so we will run the specs auto-wise. Lovely, and if we run it, it should give us the expected failures. Oh, Java startup time. Lovely. Okay, there's the failures. Lovely. Okay, now we pick up the spec. Good. And we do the window and get the split vertical. And then we pick up the core and move it like so. And so the core will be on the left and the test will be on the right. I can't seem to get these in the same order every time. Oh, well. I'll work it out. All right, so let's begin and write a test. The test should be pretty straightforward. I'm not even going to test the idea that we're going to sort things, because I think we can do that. What I am going to do is go get the 2 acceptance tests here. So there's a simple acceptance test here. Let's get that one. Okay, and we're going to take that and we're going to put it in here. And I'm going to say, let's see, def, acceptance input, test input 1 is going to be that. Okay. And we might as well get test input 2 as well. And that's going to be this. Lovely. All right, we'll put that in there and close the parenthesis. Okay. And let's see. Let's get the def input. Just for grins. Let's do it yes, let's do it this way. And the input is going to be the slurp of the input file. How nice. Okay, let's go get the input file because we want that as well, don't we? So we will go get the input file, which is going to be here. And heavens, of course, it's this massive array. Okay, copy that. Lovely. Make that go away. Now we're going to create the file, new file, input, okay, input, and we will paste our numbers in there. Lovely. Okay, make the input go away. Okay. Each of those three things is roughly equivalent in its form. All right. So now let's say defin 2 ints. We're going to turn that string into an array of ints. How are we going to do that? Well, data. This is going to be the string. Lovely. Let lines be map. String dot split lines s. Okay, so that should be all the lines. And then we should just return the map v of integer / parse int of parenthesis to lines. You do lovely, good. Okay, and let's just check that, make sure that it works. So this is actually in our tests here, right? This is a little utility in our tests. But okay, we're going to describe the input data. This is just, I'm going to delete this probably. I don't know. It should be ints. Got it. Okay. And should equal nil 2 ints of test input 1. And I believe that that's going to create me a nice list of 16 and 10 and 15 and 5. Yes, okay, fine. So that worked. I'm not even going to try to save that. That's not a useful test. Okay, next thing we want to do. I want to take a list of integers, and I want to compute the list of differences. So describe, let's call this tools, and it should calculate differences. All right, we're going to calculate the differences. So the function we're going to call is going to be get differences of, let's say, test input 1. 2 ints. No, not even do that. Let's just make a simple little list. 1, 2, 4, 7. Good. Okay, nice little list. Okay, and what should that be? And the differences should be 1, 2, and 3. Right? So the difference between 1 and 2 is 1, difference between 2 and 4 is 2, difference between 4 and 7 is 3. So that's what I should get. And this, I'm certain, is going to fail because I don't have a get differences. So, defin get differences of some list of numbers. Return nil, and that should fail horribly, right? Because 1, 2, 3, nil. Okay, so now what we want to do is we want to walk through that list calculating the differences. Okay. Is there an easy way to do that? Walk through the list calculating the differences? Well, what an interesting idea that is. I could create two lists and then subtract the lists. That's kind of clever, isn't it? So here, L1. Let L1 be the but last of numbers. So that'll be all the numbers except the last one. Yep. And let's let L2 be the rest of numbers. That'll be all the numbers except the first one. So now I have these two lists and they're exactly the same size, but they're shifted against each other. And now the difference is going to be, and I think I can do this with a straightforward map. Map minus, which one do I want to subtract? I want to subtract the L1 from I want to subtract L2 from L1. I think that's it. No. Ooh, it got negative. How interesting. Let's try L2 from L1. Oh, okay. All right, I got it. All right. I had it backwards, but okay. So this is how you get the differences. Okay, so now what we want is the sum of the difference categories. So a difference category would be a difference of 1, and another one would be a difference of 2, and another one would be a difference of 3. What we want to know is the number of difference categories. And we actually don't care about that at all. We just care about the number of 1 differences and the number of 3 differences. So, I think I can do that right here. I think I can say, well, okay. Gosh. I think I can just solve the problem here. I don't think there's much left. Here. Describe solution. Okay. Describe the solution. And I will need a little function for this. So let's do this. It should find the solution to let's see. Solve problem 1 of, let's go down here. Should equal nil. That's just the way I start things. Solve one. And let's use the same list. Well, yes, the same list. 1, 2, 4, 7. And 8, let's say. Now, we have 2 differences of 1 and 1 difference of 3. All right? Which means the number that we're looking for is 6. I believe that's right. So solve one. Let's go over here. Okay, so we're going to say let the differences be the get differences of the numbers. All right, that's fine. And then we're going to say D1 is going to be the count of the filter of equals 1 numbers. Yeah. D2 is the count of the filter of equals 3 of the number. I did that wrong. Right. Okay. And then we just return D1 times D3. And I did something terribly wrong. Let's see, what is it? Unable to resolve D3. That's because I didn't name it properly. Okay, and let's see what we've got here. Expected a 6 got 0. Okay, well, let's print the difference. Ooh, differences, Bob, differences. There we go. Expected 6 got 2. Well, that's interesting. Okay. So let's take a look at our differences just to make sure I did that right. So the differences is 1, 2, 3, 1. So I expect that to be 1 difference of 3 and 2 differences of 1. So I filtered for 1. So let's see, D1 ought to be 2 and D3 ought to be 1. Oh, Bob. Yikes. Yeah, it should be a 2. Here, let's make it a little more interesting and give it another difference of 3. 11. Okay, so now it should be a 4. Right? Let's see. Yeah, 4. Okay, good. We don't need this print one. Okay, so, let's just check to see our acceptance tests. We've got them. We might as well do them. Okay. It should. So simple. Test data 1. Okay. And that should be should equal. Oh heavens, yeah. Okay. Test data. Let's just say test data. Should solve test data. We don't need to have multiple ones. Okay, so the first one was, what does it say here? 7 differences of 1 and 5 differences of 3. So 7 times 5 is 35, right? So let's say 35 of test data 1. So solve 1 test input 1, and I've got to do the whole nonsense of what is it? 2 ints. Of test input 1, and that should work. I got 0. Why did it get 0 for that? Ooh, heavens. Okay. So I expected a 35 here. What did I do wrong? All right, so let's... well, all right, let's just do this again. Actually, let's do this. Okay. Oh, I didn't sort them. Dumb. That was the whole point of this thing. You had to sort them, right? Actually, that sort should go in here. So let's do this. Sort numbers. So that should actually be there, so that I don't actually have to do it there. Okay. And we got 1, 2, 3, 4, 5, 6 ones and 3 threes. That's what, well, no, it says 6 ones and 4 threes. That's what it counted. So it counted them correctly. Did it calculate them properly? Well, okay. What did they say? They said, in this example, when we're using every adapter, there are 7 differences of 1 jolt and 5 differences of 3. 7 of 1 and 5 of 3, but we got 6 and 4. So we're missing 1 each. And where would that be? Well, I know where it is, because there's the first adapter starts at the power output of 0. So the power output of the seat you're in has an output of 0, and then the laptop that you're going to plug it into has a difference of 3. Right, so it's got a rating of 0 and a difference of 3, right? Your device's built-in adapter is always 3 higher. So there's always going to be one more 3. And then you've got to plug it into your chair, and the chair is, you don't know what that's going to be, but it's going to start at 0. So we're going to do this. Yeah, we're going to sort it all right. Yes, fine. So let's take this, and we're going to turn that into a variable. We're going to take that and turn it into a variable. Refactor. I know how to refactor variables. Extract variable. That's Option Command V. I knew that. In this let. Good. Okay, so sorted numbers. Just for grins. We want a 0 on the beginning of it, right? So I want to prepend a 0. How do you prepend to a list, right? And is this a list or is it a vector? The output of sort is probably not going to be a vector, so let's just make it one so that we know that it is a vector. Lovely. Okay, now I want to put a 0 on the front of that. So sorted number. Let's just leave the name numbers. That's fine. Numbers is, and how do you prepend something? Prepend to a vector. We use the into function, and we say into a vector that contains a 0. Put the rest of the numbers. Good. Now, and I use sorted numbers here, so let's get rid of that. Okay, fine. So that's our adjusted numbers. And then we're going to inc D3 because we want to count the last guy, right? Okay, so now we're going to get some interesting failures. The test data got solved correctly, but we expected 4 and got a 9 on the solution. So that should be a 9 now. Okay, that's good. And let's try the bigger test case. So let's do this. It's going to be this. So we're going to say, let's just copy and paste that, right? So this is going to be solve 1 2-ins test data 2, and the answer to that one is supposed to be, let's see, 22 times 3. 22 times 10 is 220. So let's see if that's 220. And oh yes, that one worked as well. So lovely, all that did seem to work, and so let's just solve the problem now. Yeah, it describes solutions. Fine, fine, fine. It should solve problem 1. And we're going to say, okay, should equal, I don't know what, 0, solve 1, 2 ints of input. Okay. And it says got 2070. Well, okay, is that the right answer? Looks like we got 69 and 29. So if you tell me that that's, it's going to increment that by 1, so that'll be 30, right? So 69 times 30 is 2070 if you say so. But let's go and see if that is the right answer. 2070. 2070. And submit that. Oh, that was the right answer. Oh, heavens. Continue to part 2. Well, before we continue to part 2, let's clean this up just a little bit. I don't know what the meaning of this solve 1 thing is yet. So I might just leave it as solve 1. The rest of this, I think, is probably clean enough. I hate this increment. I'm tempted to put another number at the end, which is 3 plus the max. But I'm not going to do that because the increment is fine. It's just a little bit of a magic number, isn't it? Okay. Let's take a look at the second part of this problem. So I think they've laid a trap for us. I think that's what this problem is. You can see what I've done here. I've written a nice little recursive algorithm which loops around and tries to search through the network of adapters to find all the different working pathways. And this works fine. Everything works just great. My acceptance tests all pass. Oh, I left that one open. Well, here, I'll just run that for you now. Right? Everything passes, the acceptance tests all pass. Everything passes except for the actual problem. That one doesn't terminate. I let it run for an hour. Just kept right on running. So this recursive algorithm I've written is probably not the one that they had in mind. This is the little trap they've set for us. So I'm going to think more on this and get back to you. You may notice that I'm wearing different clothes now because it's the next day. Sometimes a little sleep really helps when you're solving a problem like this. You would not have wanted to watch me do this one live because you would have been watching for 5 or 6 hours as, I eventually lost my sanity. So this was a tough problem to solve. It shouldn't have been, but it was. And let me show you where I began. I showed you this one a little earlier. I've commented it out now, but this is a fairly simple, it only took me 2 hours or so to work it out, fairly simple recursive algorithm, which just computes the paths. So we've got this function here called doGetPaths. It's whenever I write a recursive function that accumulates, I put a do in front of it. So getPaths calls doGetPaths, and then doGetPath calls itself recursively. And I could not use the recur function, the closure recur function, because this is not a tail call, and you can't use recur unless you're doing tail recursion. So it's not very difficult to understand once you've worked on it for 2 hours and you've figured it out. doGetPaths simply says, hey, start here in the list of sorted adapters and go to there. So we're going to start at the beginning and stop at the end, and this is the list of adapters, the numbers, and we're going to accumulate a path. we'll just accumulate a path as we go down. So that's, one of these do functions. I like to put the word do in front of them if we're accumulating something in an argument. Okay, if we've reached the end, and the the last element of the path is the end, then we say that yes, in fact, we have gotten a path, and we return a list with that one path in it. Okay, now if we have not reached the end, then we say that the next candidate is the first in the list of numbers, and if that is more than 3 away from the start, less than 3 away from the start, then we say, okay, that's a reasonable one. We could use that one. So go ahead and get all the paths from that candidate to the end using the rest of the numbers. And, oh, by the way, take the path and conjugate it onto or take the candidate and conjugate it onto the path. Okay, so that builds up the path. And we'll put that into we'll put the path returned by this, or the paths returned by this, into found. And then we're going to also say, go get the paths that start where we started before and end where we ended before, using the rest of the numbers. In essence here, we're just skipping the next one in line, and we repeat the path. So we're assuming that, okay, since it's within range, we can use it, but we don't have to use it. There is a chance that we could skip over it, and the next one would work. And we accumulate those paths into found 2, and then we take found 2 and we merge it into found, and we call that all, and we return all. And what this does is it accumulates all the paths. Now, this algorithm works just fine. It passes all the acceptance tests. But if I run it on the main input, the one they really give us to solve, it runs for a very long time and then runs out of memory. Now, why does it run out of memory? Well, so the list of numbers they give us in the actual solution is like, several hundred long. And now give this a little bit of thought. Okay, if the average difference between the adapters is 2, it can be as small as 1, it can be as great as 3, it can't be 4 because that would stop the chain. So, okay, 2 is kind of the average distance, and if you've got, 2 and then 2 and then 2 and then 2 and then 2 a couple of hundred times, well, then you've got 2 to the couple of hundredths possible paths. You can work that out in your sleep if you'd like to, because that's a fairly disheartening number. And my algorithm here was accumulating all those 2 to the several hundredth paths. Well, of course, I'm going to run out of memory. So I backed away, and I said, okay, there's got to be a better algorithm for this. And it occurred to me that I could build a tree. And I drew the tree for the first little problem, because diagrams really help a lot. I drew the tree for the first little problem, and I saw, oh, look, yes, if I follow the paths, I can count 8 paths in there. Well, that's what I should do. So I wrote that algorithm, not realizing, of course, that it was the same algorithm, but never mind that. So here's the algorithm here. Now, I do have to say that it's a bit more elegant than the previous algorithm, and I'll explain that in just a second. So I started this the same way, and you can see the code here, and I sort the numbers, and I turn it into a vector, and I put 0 on the front of it because that's the power plug on your seat begins at 0, so you have to start at 0. And I get the last of the numbers, which would be the greatest. That'll be the end point. And then I build the tree, and then I count the paths in that tree. And counting the paths in the tree, starting from 0 and going to the end. That's how you call count paths. Now, how do you build the tree? Well, it's pretty straightforward here, once you've worked on it for several hours. Okay, so how do you build the tree? Well, all right, so given the numbers, I'm going to say, okay, find the last number, That's fine. I know I did it down here, but why pass it? You know, it's pretty simple. And then I add into the numbers two more numbers that cannot be in the chain of adapters, right? Because they're more than 3 away. And I did that just to avoid the array index out of range exceptions that these functions would have encountered. Because what I'm going to do is look ahead 3 numbers, regardless of where I am in that array, and that's all this does, right? So I get the remember I'm looping through an index here, right? So I'm going to loop through an index from range to numbers -3. So I'm not even counting those last 3 that I added in, right? And then starting at 0 and going forward, and then I run that in a for loop, and I get the 4 indexes I want. The 4 indexes are the current starting place, and then +1 and +2 and +3. So you can see that's what's going on here. And I get the numbers at those indexes. And then I make sure that they are not 3 away from the start, the index, the starting index. And I set those into 3 Boolean flags. And if those Boolean flags are true, then I add them into a growing list. So then I merge all of those nodes together. What this creates is a map which has the key of an adapter, the joltage of an adapter, and then a list of 0, 1, 2, or 3 next adapters, right? So that's kind of the tree. And then we count that tree up. Okay, so counting the tree up is really straightforward once you've spent hours on it. You count the paths, and if you know you're done if you've gotten to the end. So if the start equals the end, you've reached the end and you've found a path. That's the most important thing here. You have found a path, so you can return a 1 because you have found one path. But if you're not at the end, okay, well then get the children from the tree at this location and then loop through those children, calling count paths, starting from the child. Now that will return the number of paths found in the tree starting at that child. And the for loop will accumulate them into a list, and then we'll add them up and return them, and that will return the sum of all the paths. Typical recursive algorithm that is simple when you look at it and takes hours to work out, at least for my addled brain. Now, this worked great, worked just as well as this algorithm up here worked, and in fact, it worked rather identically to the way this algorithm up here worked, except that it did not run out of memory. On the main loop, it just ran forever, which, of course, you would imagine, because, once again, I've still got this 2 to the several hundredth problem that I'm dealing with, but, and here's the key to it all. And by the way, I cheated to find this key. I actually looked at somebody else's solution, and I saw, oh, I see what they did, and, I shot myself in the head several times, because that's what you do when you realize you've been stupid. It turns out that this function here, count paths, is called with only one variable. Tree is a constant. It never changes. End is a constant. It never changes. Only start changes. And there's only a couple of hundred starts, right? This list of adapters is only a couple of hundred long, which means that I am going to be calling this count paths function 2 to the several hundredth times with only maybe 100 possible variations. What could I do about that? Well, you see, Clojure has a very nice little facility called Memoize. Memoize takes a function and caches the result in a map keyed by its arguments. If you call it once and this map doesn't have the arguments, then it calls the function and evaluates. But if you call it again and it finds in the map that you've already called it with those arguments, it just returns that value. Okay, and what that means is that I am not going to go through this recursive depth search 2 to the several hundredth times. I'm going to go through it n times, where n is the number of elements in the list. And of course that works and gives me this number. I haven't tried this number yet. I don't know if it's the right number. I think it is, because all the acceptance tests pass and everything else passes. All right, so I'm assuming that this is the right number. Let's go find out, shall we? Okay, the moment of truth. And notice, by the way, how large that number is. How many paths were there? Let's see. That's millions. Yeah, 24 trillion. 24 trillion, yeah. I wasn't going to finish that. There wasn't going to be anyway. Yeah, okay, so let's submit this. Yes! That was the right answer. And I have finished day 10 of Advent of Code. Somewhat embarrassingly, I might add, but okay. Sometimes you get the bear. Sometimes the bear gets you.